Near Earth, sunlight makes darkness harder to measure cleanly. New Horizons went beyond that glow and exposed the universe's remaining optical light. What makes the optical universe dark, and what remains after every measurable foreground is subtracted? Nearby space looks black because a nearly empty sightline scatters little sunlight sideways into a camera or eye. Sunlit objects can blaze, while adjoining space stays dark. The cosmic question reaches farther. After local glare is removed, the optical sky stays dim, chiefly because stars have illuminated only a finite span of cosmic history. There has never been unlimited time for light from every possible distance to arrive. Expansion further weakens arriving radiation and shifts much of it toward longer wavelengths. Black, here, means faint rather than empty. A residual glow remains after identifiable sources and foregrounds are counted. New Horizons carried a camera beyond the bright zodiacal dust near the sun, aimed it at carefully chosen blank fields, and measured that remainder. Subscribe for cosmic investigations that test every foreground before naming the unknown. New Horizons was built to see Pluto from a fast-moving spacecraft. Its long-range reconnaissance imager, called LORRI, needed a narrow view, a stable optical system, and enough sensitivity to acquire a small, distant world. After the Pluto encounter, those same properties gave the camera another use. The spacecraft continued outward while the sun and its surrounding dust receded behind it. By the time of the dedicated Cosmic Background Survey, New Horizons was nearly 57 astronomical units from the sun. The survey used a vantage inaccessible to observatories near Earth. Distance mattered because the inner solar system has its own glow. Interplanetary dust catches sunlight and scatters it across the sky as zodiacal light. Near Earth, that foreground can exceed the signal sought between the galaxies. A telescope above the atmosphere escapes airglow and weather, yet it still sits inside the dusty region that produces zodiacal light. New Horizons occupied a far cleaner site. The advantage came less from a larger telescope than from a darker location. The distant location never made a raw frame synonymous with the extragalactic background. It greatly suppressed zodiacal light, while Milky Way dust, faint stars, off-axis glare, and detector electronics remained. Remoteness removed the largest familiar foreground. Survey design handled the surviving terms. A cleaner observing site could narrow the uncertainty without revealing an origin for each individual photon. From nearly 57 astronomical units, LORRI sampled clean science directions and separate calibration fields. Repeated exposures exposed cosmic ray hits and random detector fluctuations. Off-axis scattered light required source catalogs and the camera's measured scattering response. One foreground had no edge that could simply be masked. Milky Way starlight scattered by interstellar dust. The disagreement between an early field and the later survey became a test of which foreground treatment the expanded observations supported. Black on a display often represents a choice made during processing. Pixel values are mapped onto a limited range so that stars remain visible and faint structure can be emphasized or suppressed. Physical darkness is more demanding. A detector assigns counts to incoming photons and to its own electronic activity. After calibration, those counts yield a brightness with units, error bars, and a stated spectral response. The color shown on a screen carries far less information than the measured radiance behind it. Radiance describes how much power arrives from a direction. The area term in nanowatts per square meter refers to the receiving surface. The steradian term refers to solid angle, the two-dimensional spread of directions on the sky. A steradian plays a role for directions, somewhat like a radian plays for angles, though it covers an area on an imaginary sphere. Reporting power per steradian allows brightness from one patch of sky to be compared with brightness from another patch of a different apparent size. This distinction separates a total amount of light from the brightness of an extended background. A wide field gathers photons from a larger portion of sky than a narrow field. Dividing by solid angle expresses the intensity associated with each unit of sky rather than merely announcing the total caught by the detector. Dividing by collecting area similarly prevents a larger receiver from appearing to observe a brighter universe, simply because it intercepts more photons. Exposure time supplies another part of the measurement. A faint field may deliver only a small number of useful photoelectrons during a brief interval. Keeping the detector active for longer lets more photons accumulate. Random counting fluctuations become less important relative to the growing signal, while stable biases and foreground errors remain. This is why repeated exposures matter alongside long exposures. Time helps with statistical noise. Calibration confronts systematic error. An indefinitely long exposure would never solve every problem. A slightly wrong detector baseline would remain slightly wrong after hours of collection. An inaccurate estimate of scattered galactic light could become the dominant limitation once photon counting improved. More time sharpens the average of what reached the sensor. Independent calibration decides how much of that average belongs to the quantity being sought. The distinction explains why a larger set of directions change the conclusion more than a dramatic increase in exposure alone could have done. Even a capped lens can produce counts. Thermal activity and electronics create dark current and bias. LORRI included shielded detector columns that tracked their combined level. Subtracting that contribution removed an internal baseline, but the remaining photons still had multiple origins. A photon scattered by Milky Way dust enters the detector as readily as a photon that traveled from a remote galaxy. The camera identifies arrival, direction, and response. Physical interpretation comes from comparing fields, external maps, source catalogs, and calibration observations. The phrase blank field therefore describes selection, not literal emptiness. Bright stars and obvious galaxies were avoided because their glare would dominate. Fainter sources remained. Some could be masked after detection. Populations beneath the detection limit required statistical estimates based on deeper observations and source counts. Diffuse galactic light had no neat edge to mask. Its brightness had to be inferred from infrared emission by dust and calibrated against fields with deliberately varied dust levels. Bright objects were masked to define the usable sky pixels. Faint Milky Way stars, off-axis scattered light, galactic dust glow, and detector terms then required separate estimates. External galaxies were treated differently. Unresolved galaxy light belongs to the cosmic optical background, and the estimated light of bright galaxies removed by the masks had to be added back before the final background was reported. The resulting background was a remainder with a probability distribution, not a bucket of photons stamped cosmic. Every subtraction contributed uncertainty. If one foreground estimate moved upward, the inferred cosmic background moved downward. If its uncertainty widened, the range allowed for an unknown component widened too. The later survey constrained the dominant foreground directly across multiple science and calibration directions. Local blackness and cosmic blackness can now be kept separate. In the nearby vacuum, sunlight usually travels past an observer without entering a sideways line of sight. The beam becomes visible when matter redirects some of it, as molecules brighten Earth's daytime sky, or dust reveals a shaft of light. An astronaut can face a blazing, sunlit surface beside a black sky, because the intervening vacuum offers very little material to scatter sunlight toward the eye. Cosmic optical darkness concerns radiation arriving from beyond the solar system after local foregrounds are reduced. Its faint glow combines the accumulated output of galaxies across time, altered by cosmic expansion and limited by which emitting regions can have sent light to the present. A black-looking frame may still hold a precisely measured background. The visual impression of nothing and the physical measurement of something can occupy the same direction. The measurement could set only a wavelength-bounded limit. It could not declare the universe empty or settle the ultraviolet, infrared, or microwave backgrounds. The unresolved optical question was whether the budget would close once foregrounds and galaxy light were treated consistently. Yet a deeper difficulty survives beneath every careful subtraction. Galaxies fill the observable universe, and stars pour optical light into space in every direction. More distant regions occupy ever greater volumes and contain ever more potential emitters. Why, under an eternal and unchanging sky, would their accumulated light leave any sightline dark at all? The old bright sky argument begins with a calculation that seems too simple to threaten an entire picture of the cosmos. Place an observer at the center of an imagined universe filled evenly with stars. Around that point, mark a thin spherical shell at some distance. The light from any one star fades with the square of its distance. Double the distance, and its flux falls to 1/4. Yet the shell at twice the distance has 4 times as much area, so it contains roughly 4 times as many stars. The greater number cancels the dimming. A thin shell far away contributes about as much combined starlight as an equally thick shell nearby. Add another shell and the brightness rises. Keep adding shells through an unlimited stellar cosmos, and the total has no natural stopping point. A second way to express the same problem uses lines of sight rather than sums of flux. In a universe where luminous stars have existed forever and are spread without end, almost every narrow direction should eventually strike a stellar surface. Nearby stars would cover some small patches of sky. More distant stars would fill many of the remaining gaps. At sufficient depth, the sky would approach the surface brightness of a typical star. Actual night is nowhere close. Most of the celestial sphere is optically faint, even though sensitive instruments reveal a low glow between the resolved sources. The contradiction became associated with Heinrich Wilhelm Olbers after his discussion in 1823, but its essential geometry appeared earlier in work by figures including Johannes Kepler, Edmund Halley, and Jean-Philippe Loys de Chasseau. The history matters less than the premise each version exposed. Darkness places limits on the imagined cosmos that produced the bright prediction. The inverse square law, therefore, remains fully intact. It makes each remote star dimmer, while geometry supplies more stars at the same rate. Confusion often begins by following one source to great distance and overlooking the growing population at that distance. Surface brightness offers another check. Moving a star farther away reduces its total received flux, but it also shrinks the apparent area of its disk by the same inverse square factor. Wherever a line of sight finally ends on a stellar surface, the brightness per apparent area remains comparable to the original surface, apart from absorption or changes along the light path. Infinity by itself is insufficient. Space could extend without end and still present a dark sky. The bright result also requires a stellar population with no beginning, a large-scale distribution that remains sufficiently uniform, transparent propagation over unlimited distances, and sources that keep radiating long enough to fill every direction with accumulated light. A static geometry keeps distant light from losing energy through cosmic expansion. Remove any one of those premises, and the divergent sum can be cut off. Clumping stars into galaxies fails to rescue the eternal picture. At modest distances, galaxies leave broad gaps. At much greater distances, an unending population of galaxies supplies more projected disks inside those gaps. The scale of the luminous units changes, but the accounting survives. Empty regions and clusters alter the texture of the sky. If the average luminosity per volume remains positive across unlimited distance and time, irregularity alone cannot guarantee lasting darkness. Absorbing dust sounds more promising because the Milky Way visibly blocks starlight. Dark lanes cross its bright band, and thick molecular clouds can hide stars at optical wavelengths. Dust, however, is matter with a temperature. A grain that absorbs radiation gains energy. It can cool only by radiating energy away, mostly at longer infrared wavelengths. In an eternal static cosmos, bathed from every direction by an unlimited supply of starlight, dust cannot act as a bottomless drain. It warms until emission balances absorption. Optical darkness purchased by absorption reappears as thermal radiation elsewhere in the spectrum. This point separates a color change from an energy solution. Real dust profoundly reshapes the cosmic background. It absorbs ultraviolet and visible photons and releases much of their energy in the infrared. It can make a chosen optical direction faint. What it cannot provide in the classical eternal construction is permanent disposal of the incoming power. A bolometric measurement, one that counts radiation across all wavelengths, would still confront the accumulated energy. Real cosmology breaks the classical premises before such an equilibrium is reached. Stars began to form only after an early interval with no stars. Individual stars have finite lives. Galaxies change their rates of star formation as gas is consumed, expelled, heated, and recycled. Radiation travels through an evolving space-time rather than a static Euclidean expanse. The dark sky is therefore more informative than a statement about how much empty space lies between luminous objects. It reveals that the supply, travel, and history of cosmic light are finite in the directions available to observation. The most important cutoff is temporal. The universe has a finite measured age of about 13.8 billion years. Light received now can come only from events connected to the present by a past-directed path through space-time. Events whose light has had no opportunity to arrive contribute nothing to the present optical sky, no matter how much space may exist beyond them. Even inside the observable region, luminous stars were absent at the beginning. The early universe was hot, dense, and nearly uniform. It expanded and cooled for hundreds of millions of years before gravity assembled gas into the first stellar systems. Cosmic star formation later climbed, reached a broad maximum when the universe was only a few billion years old, and declined toward the present. The sky has therefore had neither infinite time nor constant luminosity to build an unlimited optical background. The age is inferred through several independent physical clocks. Measurements of cosmic expansion connect present distances with the rate at which the scale factor has changed. The microwave background constrains the composition and early conditions that determine the later expansion history. Ages of the oldest stellar populations provide a separate lower bound. Agreement among these approaches leaves no plausible interval remotely long enough for the classical accumulation of starlight from an eternal population. Finite stellar lives sharpen the result. Massive blue stars can exhaust their central fuel within millions of years. Sun-like stars last for billions. Small red dwarfs may endure for trillions, far longer than the present cosmic age. But even they entered existence at finite times and radiate at finite rates. A photon census at the present epoch includes only the light emitted so far. It cannot include radiation that future stars will produce, or radiation from sources whose past emission remains outside causal reach. The relevant boundary is the particle horizon. It marks the greatest co-moving distance from which a signal could have reached the present location since the hot early universe, given the actual expansion history. The phrase observable universe refers to this causally accessible region, not to a known edge of all space. No telescope can use present light to inspect beyond the current particle horizon, because no such light path reaches the observer now. The word distance needs care here. A photon may have traveled for nearly the age of the universe, but multiplying that travel time by the speed of light gives neither the source's present distance nor the present radius of the observable region. Space expanded while the photon traveled. A galaxy that emitted ancient light was much closer when the emission occurred. Its present co-moving distance can be far greater than 13.8 billion light-years. Under standard cosmological parameters, the radius associated with the observable universe is roughly 46 billion light-years in present co-moving distance. A past light cone supplies an intuitive description of the evidence. Nearby objects are seen after a short delay. More distant galaxies are seen at earlier stages. Looking farther means sampling earlier cosmic times, until ordinary optical observations encounter epochs before mature galaxies and stars existed. The available volume grows with distance, yet the emitting population changes as the look-back time increases. The shell calculation from the classical paradox assumed equivalent luminous shells forever. The real shells represent different eras. None of this proves that space itself has a finite volume. The entire spatial cosmos may be finite, perhaps through a global topology with no boundary, or it may extend infinitely. Current observations constrain curvature and other large-scale properties within the accessible region. They cannot turn a finite causal reach into a measurement of the total spatial extent. Darkness establishes a limit on received history, not a wall located at the rim of existence. Finite age and finite luminous history perform most of the work in resolving the classical paradox. Expansion changes the result further, but it should not replace the temporal explanation with a slogan. A universe filled with stars for unlimited time created the divergence. The real universe has hosted stars for a limited interval, with a luminosity density that evolves strongly. The optical background received now is an integral over that finite and changing past. Light moving through expanding space carries an imprint of the expansion. As the cosmic scale factor grows, the wavelength of a freely traveling photon grows with it. A photon emitted when the scale factor was smaller arrives with a longer wavelength. Since photon energy is inversely proportional to wavelength, the same photon arrives with less energy than it had at emission. Radiation that began in the ultraviolet may arrive in visible or infrared bands. Radiation that once had a thermal spectrum associated with thousands of kelvins can arrive as microwaves. Energy loss per photon is only part of the dimming. Suppose a distant source emits two successive wave crests, or two successive packets of photons, separated by a fixed interval in its own cosmic era. Expansion stretches the interval observed at the present epoch. The arrival rate slows by the same redshift factor that lengthens the wavelength. Each photon carries less energy, and fewer photons arrive per unit time. For an extended source, the relation between apparent angular area and physical area contributes additional factors. The full bolometric surface brightness of an otherwise comparable source falls as 1 plus the redshift raised to the 4th power, the Tolman dimming law. Redshift here comes from the changing scale factor along the photon's path. It is more than an ordinary Doppler shift through fixed space. For nearby galaxies, Doppler language can provide a useful approximation. Across cosmological distances, general relativity supplies the full description. The observed ratio of wavelength to emitted wavelength equals the ratio of the scale factors at reception and emission. Every stretch in wavelength, therefore, carries a direct statement about how much the universe expanded while the light was in flight. This cosmic dimming helps suppress the contribution from remote galaxies. It also moves energy between observing bands. A dark optical sky cannot be treated as an empty electromagnetic sky, because radiation absent from human vision may remain abundant at infrared, microwave, radio, ultraviolet, X-ray, or gamma-ray wavelengths. Darkness depends partly on which photons an instrument accepts. The strongest demonstration covers the entire sky. Roughly 380,000 years after the hot beginning, cosmic matter cooled enough for electrons and nuclei to form neutral atoms efficiently. Before this transition, free electrons scattered photons repeatedly, keeping the photons tightly coupled to the ionized baryonic plasma and making the universe opaque across large distances. As neutral hydrogen formed, the supply of free electrons fell sharply. Photons then traveled much more freely. The cosmic microwave background consists largely of photons last scattered around this transition. Calling this event the moment the background was created would be misleading. The radiation already existed in the hot plasma and had an extraordinarily close thermal distribution. Recombination and photon decoupling allowed that radiation to stream across the increasingly transparent universe. Small temperature and density variations at the last scattering epoch became the faint anisotropies measured across the microwave sky. Those variations later corresponded to the seeds of galaxies and larger structures. The matter and radiation near last scattering had a characteristic temperature close to 3,000 kelvins. Continued expansion stretched the photon wavelengths by roughly a factor of 1100. The observed spectrum now corresponds to a temperature of about 2.7 kelvins and peaks in the microwave range. A synthesis of measurements gives 2.72548 kelvins, with an uncertainty of 5.7/10,000ths of a Kelvin. The number sounds cold because temperature here describes the shape and energy scale of a blackbody spectrum. It should not be read as the equilibrium temperature of every object in intergalactic space. Starlight, collisions, cosmic rays, local plasma, and other radiation fields can heat matter above it. The background is instead a nearly uniform sea of microwave photons, carrying direct information from the era when the universe became transparent. Its presence resolves an apparent visual puzzle without turning the microwave sky into a stellar sky. Human eyes respond to a narrow optical band. The stretched relic spectrum supplies negligible visible brightness at its present temperature, even though sensitive microwave receivers see it in every direction. The early universe was luminous in a thermal sense, but expansion carried most of that ancient radiation far outside visible wavelengths. Expansion therefore changes both the amount and the color of ancient light received at the present epoch. It reduces photon energy, slows arrival rates, alters apparent surface brightness, and moves radiation across band boundaries. Still, the dark optical sky cannot be assigned to redshift alone. The finite duration and evolving intensity of the stellar population remain fundamental. Expansion modifies a light supply that already has a beginning and a history. The microwave background also clarifies what optical darkness can and cannot establish. A black patch between visible stars may contain microwave photons from last scattering, infrared photons re-radiated by dust, radio emission from charged particles, and optical photons too faint to register without long integration. Dark is a statement about radiance in a specified band and at a specified sensitivity. It is never a declaration that no radiation crosses the line of sight. The cosmological question eventually becomes an experimental problem. Measuring a bright star is comparatively forgiving. Its signal can rise well above the local sky, and the surrounding glow can be subtracted as unwanted background. Measuring the darkness itself reverses the task. The faint background becomes the target, while every nearby source of diffuse light becomes a contaminant whose brightness must be estimated with exceptional care. The ground is the most difficult place to begin. During daytime, sunlight scattered by molecules and aerosols makes the atmosphere bright. Night removes direct sunlight from the local sky, yet the atmosphere continues to emit. Oxygen, sodium, hydroxyl, and other species in the upper atmosphere produce airglow through chemical reactions, recombination, and excitation driven partly by solar ultraviolet radiation. Airglow varies with time, position, season, and solar activity. Even at a remote observatory with no artificial light pollution, The sky carries an atmospheric signal far brighter than the cosmic optical background being sought. Moving a telescope above the atmosphere removes most airglow, but another foreground fills the inner solar system. Sunlight strikes dust grains, shed by comets and asteroids. The grains scatter some of that light toward an observer, producing zodiacal light. From a dark site, it can appear as a faint wedge along the ecliptic before dawn or after dusk. Sensitive optical instruments see a much broader contribution. Near Earth, its intensity and spatial variation complicate any attempt to set an absolute zero for the extragalactic sky. Zodiacal light is especially troublesome because its spectrum resembles sunlight. Its broad spectrum rules out removal with a narrow emission line filter. Its brightness depends on viewing direction, solar elongation, and the three-dimensional distribution and scattering behavior of the dust. Estimates derived from inner solar system observations carry uncertainties into the final cosmic value. A small fractional error in a bright foreground can exceed the entire faint signal left after subtraction. The Milky Way adds another diffuse component. Interstellar dust absorbs and scatters light from galactic stars. At high galactic latitude, far from the bright plane, the dust is thinner but never perfectly absent. The scattered component is called diffuse galactic light. Dust also produces infrared emission that can trace where the scattering material lies. Although converting an infrared map into an optical foreground requires careful calibration, variations in grain properties, illumination, and geometry can change the relation across the sky. Resolved stars can be masked, but their influence extends beyond their visible pixels. Telescope optics scatter a fraction of bright starlight into broad wings and off-axis patterns. A bright source outside the detector's field can still contribute stray light. Catalogs help estimate this signal by supplying positions, magnitudes, and colors, while instrument measurements describe how light spreads far from the source. The faint wings from many stars add up. Below a detection threshold lies a population of faint galactic stars. None may be bright enough to identify individually in a short exposure, yet their combined flux raises the mean sky level. Star count calculations estimate this unresolved contribution. Similar reasoning applies to external galaxies. Bright galaxies can be detected and masked. Fainter galaxies remain blended into the diffuse background. Their integrated light belongs partly to the target, because the combined emission of galaxies across cosmic history is a principal component of the cosmic optical background itself. The measurement must therefore distinguish light from identifiable sources in the chosen field, light scattered into the instrument, and the integrated extragalactic signal the experiment aims to preserve. Deep imaging and absolute photometry answer related but different questions. A deep exposure can reveal galaxies many orders of magnitude fainter than the naked eye, yet its processing often removes a broad, uniform glow along with electronic offsets and local sky. Absolute photometry must retain that uniform component and attach physical units to it. The instrument needs a stable zero point as much as sensitivity. A beautiful deep field can catalog sources without settling how bright the entire field was before its background was normalized. Even the term background can hide two different operations. Conventional imaging often measures a local sky value beside an object and subtracts it to recover the object's flux. Absolute background work needs the sky value itself in calibrated physical units. Any electronic bias, dark current, flat field error, sensitivity drift, or scattered light correction can imitate a weak diffuse glow. Repeated exposures and multiple fields help reveal such systematics, but the foreground uncertainty usually sets the hardest limit. Earth orbit offers stable instruments and freedom from most atmospheric emission, yet it remains embedded in the interplanetary dust cloud. A clean measurement calls for greater distance from the Sun, where zodiacal scattering falls dramatically. It also calls for fields chosen away from bright stars and dense galactic dust. An instrument with well-characterized stray light and independent tracers for the residual Milky Way foreground. The ideal observation points toward regions that appear almost empty, then treats every detected photon as a question of origin. This is why the darkness between stars cannot be established by taking an ordinary image and reading the value of its black pixels. Display software selects a black point. Detectors add offsets. Local foregrounds dominate the raw exposure. The desired quantity emerges only after calibration and a disciplined accounting of airglow, interplanetary dust, galactic scattering, stellar contamination, and the combined light of galaxies. Cosmic darkness is measured as a small remainder, and the credibility of that remainder depends on how completely the brighter nearby contributions have been constrained. By the time New Horizons reached the outer solar system, the bright zodiacal foreground surrounding near-Earth observatories was vastly weaker, creating an unusually clean sight for optical background work. The instrument that made the experiment possible had been built for reconnaissance, not background cosmology. The Long-Range Reconnaissance Imager, or LORRI, was designed to find distant targets, guide a fast spacecraft, and resolve the surfaces of Pluto and its moons during a brief encounter. Its 20.8-centimeter telescope focuses light onto a sensitive black and white detector. There are no color filters to select narrow bands. For the cosmic background analysis, its response covers roughly 0.4 to 0.9 micrometers, with a pivot wavelength of 0.608 micrometers. This is the broad optical range where ordinary starlight and galaxy light are prominent. Pluto demanded a camera able to see faint detail while New Horizons approached at high speed. The same sensitivity later gave LORRI another use. Once the primary flybys were complete, its view could be directed away from bright planets, nearby stars, and the dusty plain of the Milky Way. Empty-looking patches of sky became scientific targets. LORRI also brought a long calibration history. Repeated in-flight measurements found no detectable change at the 1% level in its sensitivity or optical performance over many years. Stability cannot reveal the origin of the sky glow, but it makes comparisons among separated fields more meaningful. A shift associated with direction is less likely to be confused with a camera whose response has drifted unpredictably. This turns New Horizons into an accidental observatory, a spacecraft dispatched to examine worlds at the edge of the planetary system can also test the accumulated visible light of cosmic history. The target extends beyond any particular galaxy. It is the combined radiance left after identifiable foregrounds are removed from a dark field. This quantity is called the cosmic optical background. It includes light from galaxies, whose individual images may be resolved, galaxies too faint or distant to isolate, and any genuinely diffuse optical emission between them. Every generation of stars that released visible light can contribute, provided those photons still arrive in LORRI's band. The measurement asks how much red-shifted optical radiance reaches the present in that band, and whether the reconstructed population of galaxies can account for it. The background compresses an enormous history into one present-day intensity. Nearby bright galaxies contribute alongside extremely distant systems, whose light has been stretched and dimmed. Stars that no longer exist can still contribute photons now crossing the solar system. Diffuse stellar material outside conventional galaxy boundaries may contribute as well. Absolute brightness cannot separate those histories, but it can test whether their combined energy agrees with the universe reconstructed from galaxy surveys. An exposure of a dark field begins as a total, not an answer. The detector counts light arriving from every source within its sensitivity and adds instrumental signatures of its own. The analysis must first establish the camera's zero level, reject contaminated pixels, correct known artifacts, and convert detector counts into physical radiance. Only then can the astronomical subtractions begin. Resolved sources are the most visible complication. Stars and galaxies inside the field occupy recognizable pixels, so masks can exclude their direct images. Masking must reach beyond each bright center, because a telescope spreads point source light into a point spread function with faint wings. If a mask is too small, those wings elevate the apparent background. If it is unnecessarily large, too little clean sky remains for a precise mean. Objects outside the frame matter as well. Light from bright stars can enter at large angles and scatter through the telescope. Their locations and brightnesses are known from catalogs. LORRI's response to off-axis illumination can then estimate how much scattered starlight reaches each science field. Galaxies outside the frame make a smaller related contribution. None appears as a neat object in the final image, yet their combined scattered light changes the measured sky level. The next correction comes from sources within the frame that fall below the detection threshold. A galaxy can be real, optical, and extragalactic, while remaining too faint to mask individually. Faint Milky Way stars also escape direct detection. Population counts and luminosity distributions estimate their combined radiance. These sources differ in interpretation. Unresolved foreground stars must be removed. Unresolved external galaxies belong to the cosmic optical background, even though later comparisons ask how much of that background known galaxy populations should produce. Diffuse galactic light presents the hardest subtraction. Interstellar dust grains in the Milky Way scatter the galaxy's radiation. The resulting glow has no sharp edge and can vary across the sky. Avoiding the bright galactic plane helps, but high latitude never means zero galactic dust. An optical image alone cannot reliably label each faint photon as galactic or extragalactic. Far infrared maps provide the essential tracer. Dust that scatters optical starlight also emits thermally at much longer wavelengths. After estimated cosmic infrared background emission is removed, one Planck band near 350 micrometers and another near 550 micrometers trace the galactic dust. Their correlation with LORRI brightness can calibrate the diffuse optical contribution while accounting for latitude-dependent scattering geometry. The conversion remains empirical because dust temperature, grain properties, illumination, and geometry affect the relation. This is why field selection and calibration fields are central to the result. A single exceptionally clean field may minimize galactic dust, but it offers little power to determine how optical brightness changes as the dust tracer changes. Many fields spanning a controlled range of dust intensity allow the relationship to be measured from the survey itself. The calibration then depends less on importing a universal conversion from another instrument or another region of sky. The accounting can be expressed without pretending it is simple arithmetic. Start with the calibrated source-masked sky. Remove scattered light from objects beyond the field, faint Milky Way stars, hydrogen alpha emission, and the diffuse galactic contribution. Add back the estimated direct light of external galaxies removed by the masks. The result is the cosmic optical background in LORRI's broad band. Order matters conceptually even when the algebra is linear. Direct source masks define which pixels contribute to the mean. Corrections for light scattered into those surviving pixels then modify the sky estimate. Foregrounds predicted from catalogs and external maps are applied with their own covariance. Only after the observational quantity has been defined consistently across every field can the values be combined. A mean formed too early can conceal differences that would otherwise expose a faulty correction. Each term has a statistical component and a systematic component. Statistical uncertainty reflects finite exposures, detector noise, and field-to-field variation. It can often shrink when more independent images are combined. Systematic uncertainty follows assumptions shared by many fields, including photometric calibration, the off-axis scattering correction, or the conversion from far infrared dust emission to optical diffuse light. Repeating the same observation cannot automatically remove a shared bias. The final uncertainty carries more information than a bare brightness. Two analyses can begin with similar LORRI images and reach different cosmic values if their estimates of diffuse galactic light differ. A residual can appear statistically precise while remaining vulnerable to a foreground calibration. The reliability of the cosmic inference depends on whether those shared effects have been tested with data capable of separating them. Known galaxies provide an externally estimated benchmark. Deep surveys count galaxies down to extremely faint limits and measure their flux. Extrapolations estimate the contribution below those limits. Integrating this population yields the integrated galaxy light. It predicts how much of the cosmic background established galaxies should explain, while sharing some assumptions about missed flux and faint populations with the wider analysis. The difference between the measured cosmic optical background and estimated integrated galaxy light is sometimes called an anomalous component. The name describes a remainder, not a discovered substance. A positive value could indicate missed light in the outskirts of galaxies, galaxies too faint for present counts, genuinely diffuse emission, or an imperfect foreground correction. More exotic proposals can be tested only after ordinary astronomical and instrumental explanations survive stronger observations. Units make these levels sound abstract. A nanowatt is 1/1000th of a watt. The reported radiance is expressed in nanowatts per square meter per steradian, a measure of power received per collecting area from a given angular extent of sky. The values are tiny, but a background measurement averages across many pixels and repeated exposures. Precision comes from combining weak signals, stable calibration, and fields chosen to suppress avoidable contamination. The pivot wavelength also deserves attention. LORRI gathers a broad optical band rather than separating a full spectrum. A quoted intensity at one representative wavelength summarizes that response under an assumed spectral convention. One broadband value leaves the color of any excess unresolved. This limitation shapes every interpretation. A single band brightness can expose a mismatch between the sky and galaxy counts, but it offers limited information about the source of the mismatch. Multiple fields improve spatial discrimination. Measurements at other wavelengths improve spectral discrimination. Agreement between independent methods matters because each sees a different combination of signal and foreground. The deep heliocentric location makes LORRI unusually powerful, yet distance alone confers no immunity from error. The Milky Way remains wrapped around the entire sky. Its unresolved stars and dust continue to contribute. The telescope has a measurable response beyond its nominal frame. Detector calibration still matters. The strength of the experiment lies in making those contributions explicit and attaching uncertainty to each one. Once those terms are stated, the meaning of darkness changes. Black is no longer a visual impression or a zero on a display. It is the small radiance remaining after a brighter collection of local, galactic, and instrumental contributions has been estimated. The next question is whether that remainder matches the summed output of known galaxies. In 2022, one carefully selected field produced an answer that appeared to leave something substantial behind. The 2022 analysis used a high galactic latitude field selected to reduce two major contaminants. Infrared maps indicated relatively weak diffuse galactic light, and the pointing also minimized scattered light from bright stars outside LORRI's view. New Horizons was 51.3 astronomical units from the Sun, far beyond the strong zodiacal foreground surrounding Earth. The raw total sky brightness in that field was 24.22 plus or minus 0.80 nanowatts per square meter per steradian. Raw matters here. This was the calibrated mean of the source-masked sky pixels before the remaining diffuse, unresolved, and off-axis foreground terms were removed. It was never presented as the cosmic optical background. The analysis subtracted scattered light from stars and galaxies beyond the frame, faint galactic stars, diffuse galactic light, and the hydrogen and singly ionized helium-2 photon continua. It then restored 1.70 plus or minus 0.07 nanowatts per square meter per steradian for the flux of masked bright galaxies. The resulting cosmic optical background was 16.37 plus or minus 1.47 nanowatts per square meter per steradian. Known galaxies were expected to contribute about half of that value. Subtracting the estimated integrated galaxy light left 8.06 plus or minus 1.92 nanowatts per square meter per steradian. The remainder was comparable in brightness to all the integrated galaxy light used in the comparison. Under the stated foreground treatment, zero excess was strongly disfavored. This result created a real scientific tension. It did not identify a source. The measurement offered one broad optical band and one especially clean field. An extra component could have arisen from light missed around known galaxies, from populations below survey limits, or from diffuse stars between galaxies. Papers also examined more speculative sources, including decaying dark matter particles capable of producing optical photons. Such proposals were conditional explanations for a measured remainder, not detections of dark matter. The later survey identified a specific problem in the earlier foreground estimate. The 2022 analysis used the IRIS 100 micrometer map and applied a latitude-dependent correction for what appeared to be residual zodiacal emission. The 2024 team concluded that the trend instead came from an extended zone of high-latitude galactic dust overlapping the ecliptic, treating that emission as zodiacal contamination had reduced the far-infrared dust tracer and caused the optical diffuse galactic light in the original field to be underestimated. The new analysis stopped applying that correction. It also replaced the single-band estimator with a relation using Planck measurements at 350 and 550 micrometers, calibrated across the science and dedicated dust fields. In the reanalysis, the diffuse galactic light, assigned to the original field, rose from 2.22 plus or minus 1.00 to 4.54 plus or minus 0.95 nanowatts per square meter per steradian. The foreground reassignment could leave the cosmic background securely detected while sharply reducing the anomalous remainder. The target for a stronger experiment was therefore precise. More sky positions had to sample enough variation in galactic dust to calibrate the optical to infrared relation, rather than merely extending the exposure on one clean direction. An apparent anomaly can reveal which uncertainty dominates the inferred residual. The response is a survey designed to vary that foreground deliberately. A cosmic excess should persist when the foreground relation is constrained across many independent directions. A shared foreground error should move with the improved estimate. Repeating only the original pointing would mostly reduce random noise. A longer stack could narrow the precision around the same foreground assumptions and make the result appear more decisive without testing its most vulnerable term. New directions add information of another kind. They allow a signal expected to be nearly uniform to be distinguished from a galactic contribution that changes with dust intensity. The distinction matters because both outcomes carry information. A persistent excess would demand additional astrophysics beyond counted galaxies. A reduced excess would reveal how difficult absolute sky photometry remains, even at the edge of the solar system. The follow-up traced the result to the foreground treatment that the enlarged survey was built to test. The completed survey combined the existing test field with 15 additional high galactic latitude science fields, making 16 in total. 8 more fields were observed specifically to strengthen the diffuse galactic calibration. The resulting program could test whether the darkness left after subtraction was stable across the sky or had been partly shaped by the Milky Way foreground. The expanded field set treated sky diversity as part of the instrument. The science directions kept diffuse Milky Way emission and scattered light from bright stars relatively low, while the calibration pointings sampled more dust-traced emission. One dark direction no longer had to support every subtraction. Once the estimated cosmic infrared background was subtracted from the Planck maps, the remaining 350 and 550 micrometer intensities traced galactic dust. The analysis related those values to LORRI brightness across the combined field set while accounting for the latitude-dependent scattering geometry. This self-calibrated indicator revised the most influential foreground in the earlier analysis. The survey still required the other corrections. Stars and galaxies bright enough to detect were masked. Scattered light from bright objects outside each field, faint galactic stars, hydrogen alpha emission, instrument behavior, and statistical variation remained in the uncertainty budget. Estimated light from bright external galaxies, removed by masking, was added back to the cosmic total. More fields made it possible to test these terms more consistently and reduce dependence on a single line of sight. After the foreground corrections, the cosmic optical background was measured at 11.16, plus or minus 1.65 nanowatts per square meter per steradian, at the pivot wavelength of 0.608 micrometers. The total uncertainty combined a systematic contribution of 1.47 with a random contribution of 0.75. The detection of the cosmic background itself reached 6.8 sigma. Sigma here expresses the measured signal in units of its uncertainty, so a value this large makes the existence of the optical background secure. The galaxy comparison changed most. The estimated integrated intensity from background galaxies was 8.17, plus or minus 1.18 nanowatts per square meter per steradian. Subtracting this estimate from the measured cosmic optical background left 2.99, plus or minus 2.03. Within that uncertainty, the remainder was compatible with zero. The residual's uncertainty had a systematic component of 1.75 and a random component of 1.03 nanowatts per square meter per steradian. The systematic term remained larger. This detail prevents an overconfident reading. The survey did not prove that every optical photon had been assigned to a cataloged source. It found no statistically significant need for an additional optical component beyond galaxies. The positive central remainder reached only 1.47 sigma, far below the significance required to establish an additional component. By contrast, the full cosmic optical background was securely detected. These are separate statements. Extragalactic optical light is real, while the evidence fails to establish an extra component beyond galaxy light. The simplest interpretation is correspondingly restrained. The cosmic optical background can be completely due to galaxies. Some of their contribution arrives from sources already counted in deep images. Some depends on corrections for flux outside standard apertures and extrapolations below detection limits. The measurement and the population estimate now overlap within their uncertainties. The downward revision was not simply the reward for averaging more directions. The expanded survey corrected the earlier 100 micrometer treatment, adopted the more precise two-band Planck dust tracer, and calibrated its relation to optical diffuse light across the enlarged field set. The original field was also reprocessed with an updated instrumental pipeline that modeled a count rate-dependent decaying background. Two linked estimates moved. The instrumental correction lowered the reprocessed total sky level in the original field from about 24.22 to 22.82 nanowatts per square meter per steradian. The revised dust treatment assigned more of the remaining radiance to the Milky Way. The later analysis therefore supersedes the earlier foreground inference, rather than merely presenting an equally valid alternative. The revised measurement also sharpens the meaning of the cosmic dark sky. The optical background remains firmly detected, Yet ordinary galaxies can supply nearly all of it. The darkness between resolved objects no longer demands an additional optical component, comparable in LORRI band radiance to the integrated galaxy light. Field-to-field agreement gives the survey another advantage. A truly isotropic cosmic component should remain after galactic foregrounds change from direction to direction. Dust-scattered light should track the far infrared tracers. The expanded observations separate those behaviors more effectively than one unusually clean field. Darkness becomes a correlation experiment, not merely the brightness of a single black patch. The calibration fields are part of the cosmic measurement, even though they were selected to study a foreground. Their extra range in dust brightness helps determine how much optical light accompanies a given far infrared signal. The cleaner science fields then apply that relationship, where the desired cosmic term is easier to see. A foreground is constrained where it varies and removed where it is weak. Once an unexplained optical component falls below statistical significance, the measurement changes purpose. It supplies a maximum allowance that every uncounted source must share. The positive central residual reached only 1.47 sigma, and systematic uncertainty remained larger than random uncertainty. Longer exposure can reduce counting noise, while stronger limits depend chiefly on improved foreground discrimination. The allowance applies to diffuse emission and to sources too faint or extended for ordinary catalogs. Outer galaxy wings, ultra-faint systems, and stars stripped into galactic halos can all add optical radiance. Integrated galaxy light estimates already correct for some missed flux, so every larger aperture correction leaves less space for a separate diffuse population. Deep imaging and absolute background photometry constrain opposite sides of the same census. One estimates what catalogs miss, and the other limits the total available after local and galactic light is removed. Proposed primordial populations face a band-specific restriction. Radiation from the earliest stars begins largely in the ultraviolet. Then expansion shifts part of it into optical and infrared wavelengths. Only the portion arriving inside LORRI's response enters this bound. Formation history, spectrum, dust absorption, and redshift distribution determine how much of any early population appears there. Hypothetical particle decay is constrained in the same conditional way. Earlier optical excess values motivated calculations in which axion-like particles or other dark matter candidates produced visible photons. The smaller residual narrows the combinations of mass, lifetime, abundance, decay channel, and spectrum that can fit. The bound reaches proposals that place enough radiation inside LORRI's optical band. Predictions centered elsewhere belong to measurements at those wavelengths. Spatial and spectral information can separate origins that one broadband intensity leaves entangled. Faint halo light should correlate with large-scale structure. Diffuse galactic light should follow dust tracers. Instrumental scattering should vary with bright sources outside the field and with pointing geometry. A narrow decay feature would carry a different color from redshifted starlight. A small total allowance makes these patterns more useful because every candidate must fit within a limited amplitude. One independent LORRI analysis keeps the optical question open at the level of measurement agreement. Teresa Simons and collaborators used archival New Horizons observations, acquired at distances out to 47 astronomical units, and developed their procedure with part of the data hidden from final evaluation. They reported a cosmic optical background of 21.98, plus or minus 1.23 statistical, plus or minus 1.36 calibration nanowatts per square meter per steradian. The archival value lies well above the dedicated survey result. Different data selections and treatments of diffuse galactic light, scattered light, masks, calibration, and field suitability can shift an absolute background measurement. The dedicated 16-field program remains the strongest synoptic baseline because its observations and 8 dust calibration pointings were designed for this question. The blinded archival analysis remains a genuine unresolved discrepancy rather than a result to omit. Common fields processed through both pipelines would expose where the values separate. Matched masks, catalogs, wide-angle scattering corrections, and dust estimates could be compared term by term. A future camera beyond the zodiacal cloud could add several optical colors: mist galaxy light, dust-scattered Milky Way light, particle decay, and instrumental scatter predict different spectral or spatial behavior even when their total brightness is similar. The visible band result, therefore, supplies a restrictive but conditional boundary, not universal closure. The neighboring ultraviolet sky tests a different detector, different foregrounds, and different photon sources. A residual compatible with 0 applies only to LORRI's optical band. A detector responsive to another part of the electromagnetic spectrum receives a different sky. Darkness is a relationship among direction, wavelength, sensitivity, and the foregrounds that must be removed. The human eye samples a narrow interval in which stars emit strongly and interstellar dust, both blocks and scatters their light. Dust absorbs a portion of the ultraviolet and visible radiation produced inside galaxies. The grains warm and return that energy at infrared wavelengths. Across cosmic history, this reprocessed starlight accumulates into the cosmic infrared background. A region that looks empty in visible light can carry thermal emission from dust in distant galaxies, while nearby interplanetary and galactic dust can make the infrared foreground far brighter than the extragalactic signal. Darkness creates none of the infrared background's energy. Much of it is familiar stellar radiation after absorption and re-emission at longer wavelengths. Its spectrum preserves information about obscured star formation, the temperatures of dust grains, the redshifts of the galaxies that heated them, and changes in dust across cosmic time. Visible and infrared measurements are complementary accounts of the radiant energy released as galaxies grew. Removing visible light from a line of sight can shift the energy elsewhere in the spectrum rather than eliminate it. At still longer wavelengths, the sky carries a background with a very different origin. The cosmic microwave background is the cooled thermal radiation released when the early universe became transparent. Its spectrum is extraordinarily close to a black body. Microwave instruments find this radiation in every direction, including directions that appear black to an eye or an optical camera. The microwave background contributes essentially no visible glow because its photons have been stretched to much longer wavelengths by cosmic expansion. It belongs to the same electromagnetic spectrum, but it traces an epoch before stars and galaxies produce the optical and infrared backgrounds. The dark night sky can therefore coexist with an almost uniform sea of microwave photons. Visual blackness says only that the arriving radiance inside the visible band is too weak for unaided sight. Comparing these backgrounds requires attention to what each quoted intensity represents. LORRI reports a broad optical measurement at a pivot wavelength. Infrared surveys divide a much wider thermal spectrum into bands. The microwave background is described most precisely by its temperature and blackbody spectrum. Ultraviolet studies often quote photons per unit wavelength as well as energy intensity. Equal numerical values in nanowatts need not imply equal photon counts, because an ultraviolet photon carries far more energy than a microwave photon. No single brightness number ranks the entire sky without a wavelength interval and a detector response attached to it. Ultraviolet radiation provides a more complicated test. Hot stars produce it efficiently. Neutral hydrogen absorbs it strongly. Interstellar dust scatters it. Ionized gas emits it, and the solar system adds foreground lines that can contaminate measurements made near Earth. A faint ultraviolet background can contain galactic and extragalactic contributions, whose relative strengths change sharply over intervals far narrower than LORRI's optical band. New Horizons carried a second instrument suited to this problem. The ALICE ultraviolet spectrograph measured 25 high galactic latitude targets at a heliocentric distance of about 57 astronomical units. Much of the interplanetary gas and dust responsible for troublesome near-Earth foregrounds then lay far behind the spacecraft. ALICE could examine the diffuse ultraviolet sky under conditions unavailable to observatories near Earth. The analysis concentrated on two far ultraviolet intervals. One extended from 912 to 1100 angstroms. The other ran from 1400 to 1800 angstroms. The separation between them avoided the most difficult region around the intense Lyman alpha emission of interplanetary hydrogen and instrumental scattering associated with it. The shorter interval reached down to the Lyman limit, where photons become energetic enough to ionize neutral hydrogen. Each high-latitude direction still contained Milky Way dust. The ultraviolet brightness was compared with reddening inferred from Planck observations. Dustier directions were brighter because dust scatters radiation from hot galactic stars. Extending the measured relation towards zero reddening provided an offset, the ultraviolet brightness remaining when the dust-correlated component was removed. This intercept could include unresolved galaxies, faint stars, emission from ionized gas, and any other contribution that lacked the same correlation with dust. At 1000 angstroms, the offset was 221 plus or minus 11 photon units. Expressed as a monochromatic energy intensity, it was 4.4 plus or minus 0.2 nanowatts per square meter per steradian. This was the first firm detection of such an offset in that short wavelength interval. The result became possible because ALICE observed where the interplanetary hydrogen foreground was far weaker than it is near Earth. The 1500 angstrom measurement produced an offset of 264 plus or minus 24 photon units, equivalent to 5.3 plus or minus 0.5 nanowatts per square meter per steradian. The longer wavelength value agreed with earlier measurements from the Galaxy Evolution Explorer. Its persistence at that great distance also indicated that little of this 1400 to 1800 angstrom offset originated within the solar system. A photon unit here means 1 photon per square centimeter per second per steradian per angstrom. It describes a spectral surface brightness rather than the total power across the entire ultraviolet interval. Converting it to nanowatts uses the energy carried by a photon at the stated wavelength. Quoting both forms lets the Alice offsets be compared with earlier ultraviolet work, while also placing them beside optical and infrared energy intensities. Known sources can plausibly provide about half of the measured ultraviolet offsets. Integrated light from unresolved galaxies contributes. Faint stars below masking limits add more. Ionized gas produces line and continuum emission. Warm hydrogen in the galactic halo can emit a 2-photon continuum after atomic excitation. Estimates for all of these terms carry uncertainties, and their sum still falls short of the observed intercepts. The remainder is unidentified. It has not been assigned to an exotic particle or a new cosmic population. Instrumental scattering, incomplete source estimates, calibration uncertainty, and imperfect separation of galactic emission remain live possibilities alongside additional astrophysical emission. A positive offset establishes a measurement problem. Its origin requires observations able to distinguish candidate spectra and spatial correlations, rather than a preferred name attached to the leftover intensity. Alice also searched below the Lyman limit, at wavelengths shorter than 912 angstroms. No flux was detected there. The reported upper limit was 3.2 plus or minus 3.0 photon units. Neutral hydrogen absorbs ionizing ultraviolet photons so efficiently that this part of the spectrum probes a different propagation regime from the detected intervals above the limit. The non-detection is therefore compatible with an ultraviolet glow at 1,000 and 1,500 angstroms. Changing wavelength changes what can cross interstellar and intergalactic space, what local matter adds, and which cosmic era dominates the signal. The ultraviolet offset remains unidentified. Its uncertainty belongs to a different band, detector, and foreground problem, so it cannot refill the optical residual, and the optical result cannot erase it. Darkness has become a boundary condition. Visible light sources must fit inside a residual consistent with zero, while ultraviolet space still carries a glow whose origin remains unsettled.